So this is how the sequence theory has evolved, okay, in two different parts. One is understanding why a sequence doesn't converge and converge or converge, the puzzles of it. Another one is finding the limit, the techniques of finding the limits. So what's there? Let's see. Okay. So in my personal teaching arsenal today, I have another thing left. That is, like it combines. It's actually a part of this puzzle thing. So you'll understand. We'll take examples, lots of examples of sequences, and we'll understand what it means to diverge or not convergent, diverge to infinity or minus infinity, just normal diverge. What does it mean that, I mean, if a sequence doesn't go to infinity or minus infinity, or if it doesn't go to a specific limit, what does it mean? Diverge normally and convergent. This will help you in all those understanding of the future. It's like a puzzle format of today. So you'll not learn how to find a limit, but you will learn how to uh, like understand the puzzles, why it doesn't happen. Great. So this type of sequence are important: bounded, monotone. As you can see, if you see, I've seen the graph I have shared in the group yesterday. There's something like monotone after a certain time, fully oscillatory, and something called oscillation height. So these three concepts are very important to understand what's happening inside the sequence, because everything is determined by that, right? So we'll learn this results later on, that I know with examples and stuff, that convergent sequences are bounded. Okay. We'll learn this in our course. Don't worry. I'm just telling you the examples so that you understand the basic ideas. Like if it's a convergent, probably it will be bounded, because understand it's going to a certain point. That means a certain point is going towards this. After a certain point, it's inside this interval. That means already it's bounded, and till this point, there are finitely many objects, finitely many stuffs. So of course, dono mila ke, like combining both of them, like it should be bounded. So what I will do is this. Let's find out examples. So can I give an, so what is the meaning of the bounded sequence? Bounded sequence means there exists a name greater than 0, a real number, such that mod of n is always less than n. That means, yeah, that means the positive value, like the absolute values of n is always less than n, greater than 0, of course. So that's the basic idea. Bounded. That means it's always bounded up and stays up, bound like this, between which it always lies. Monotone. Like something is increasing or decreasing, essentially it's like nothing but if n is greater than equal to n minus 1 for all n, or n is less than equal to n minus 1 for all n. Actually, it's like a non-decreasing, non-increasing thing, right? This is the monotone. Monotone after a certain time. Okay, let's give examples of this. An is equal to sine n. It's bounded. So you can see any convergent sequence is bounded. So n equal to 1 by n. n equal to sin n by n. Lots of examples. N equal to whatever, e to the power minus n. Unbounded. It's a bounded. Unbounded is n equal to n. N equal to e to the power n. N equal to n square. N equal to e to the power n by n. Something like this. So you can find this out. So these are all unbounded. Okay. You can prove it's unbounded. Monotone sequence. Monotone sequence is easy to understand. 1 by n is monotone sequence. Okay. Uh, one by n square, 1 by n cube, anything. Okay. More you can understand. Like if you take a n to be any f of n, where f is increasing or decreasing, you will get it a monotone sequence. And if a is not increasing or decreasing, it's not a monotone. Okay. If f is not increasing or decreasing, non-monotone. Simple. Now you take any increasing or decreasing function, right? Now what happens? Also, why are these two properties are important? These two properties are important because understand that let's say you have a sequence here and it's increasing, let's say like this. But you know it's bounded like this. It's bounded like this. You know that. That means this sequence cannot increase, infinitely often, right? Its sequence cannot increase or decrease just like that. So therefore, it means that at some point it will get stable. At some point the limit will converge. Limit will exist. Okay. So this is the basic idea that one interesting result is bounded plus monotone. This will give an idea that this will converge. The sequence converges. We'll learn this in more details and with examples in later classes. But I'm giving an overall idea what's happening, what's going on. We'll go towards that. Like it's so therefore bounded and monotone. These two concepts are very important. But what happens outside that? So let's take a sequence. Fn is equal to n to the power 1 by n. Okay. Just give me a minute. So if you draw the sequence, this will come out something like this. This is the line 1. You will see it will come out to be something like this. The function will turn out to be this is the x into x, fx is equal to 1 by x to the power 1 by x function. That means the points like this one, probably it will be like this. Why I'm very particular about this, I will let you know. Because the maximum happens at e to the e. Okay. So there should be e is between 2 and 3. So therefore I am just writing it like this. It's 1. So therefore you can see that this is this, the 3 to the power 1 by 3, 4 to the power 1 by 4, 5 to the power 1 by 5, and it carries on. And it goes towards 1. Right. So now this you understand that after this point, after this point, it's bounded. You can see in some sense, right? The sequence is bounded after this point, but it's not, bounded and monotone. Monotone plus bounded, but this is not bounded and monotone all over. Like it's bounded but not monotone, right? So therefore, this type of sequence is, it's actually, so it's an interest in long-term behavior. So in the long term, after a certain time, the long time is becoming monotone and bounded. Hence, it's also convergent because we know monotone plus bounded is convergent. That's why we define something called monotone after a certain time. Okay. So this is monotone after a certain time. Modern after a certain time, this is, you will not never find this in literature in any book. Okay, I have just like tried to make this up myself so that it helps you to understand. So therefore I request, probably I will write a book in the future. That's a different issue, but you should understand this. This is the dynamics of how it's happening. So if there exists, yeah, Meenakshi,
Sir, can you explain me the concept of monotone once again, sir?
monotony is nothing but it's like the sequence is increasing or it's like decreasing every single step. The value of the sequence is decreasing or increasing. You understood?
Yes, sir. By this graph, what we see is the sequence is decreasing right now, sir, for the red dots.
Yeah, in the after the certain time, after in this yellow region, after a certain time, it's decreasing. You're right. It's monotone.
Okay, sir. Thank you, sir.
My pleasure. So that means there exists certain, certain aim, uh, such that for all n greater than equal to m, an is monotone. That means after a certain time, it's monotone. Right. After a certain time, it's monotone. That's interesting. That's interesting. So what happens if a sequence is not monotone? Essentially, how can a sequence go towards a limit? It can either go like this. So this is the question I'm addressing today. How can a sequence go like this? It can go like this. It can go like this. This is monotone bounded. It can go like this. I've shown, right? It can also go like this. Still, it's monotone after a certain time. Understand? Blue is monotone after a certain time. Monotone after dot dot dot. Black is monotone. Of course, these are bounded because we are assuming it's convergent. So of course, all of them are bounded. Okay. But after bounded, what happens? So boundary is the first criteria. Okay. Boundary is the first criteria. After that, what happens? Then you check like monotone or bound. Now the final thing is that what happens? We have already seen examples like this. Where it's neither bounded nor it's not bound. It's bounded but not monotone. So I call this fully oscillatory because it's oscillatory. After a certain time, it becomes like this can become like this. You can find functions like this. Okay. But this is monotone after a certain time. It's not oscillatory, fully oscillatory. So fully oscillatory are like this. There are no other type of functions that you can have that can converge to this, right? Either after a certain time, the sequence will be monotone. After a certain time, it will be like it will totally monotone. After a certain time, it will be monotone, or it's not monotone. That means what? If it's not monotone, that means after a certain time, it's already oscillating, like up and down, up and down, up and down. That means after a certain, every single time, it's oscillating up, down, up, down, up, down, up, down. Like since it's monotone after a certain time, that means it's oscillatory. So therefore, this three type of sequences are there that is very important that can converge. Okay, that can converge. If it's not bounded, then of course it is either diving into. So that's where the picture comes up. Okay, That's where the picture comes up. So therefore, this is where the picture comes. So there is a sequence AN. So first we check bounded or not. If it's not bounded, something happens. But if it's bounded, we will learn this in details. Then we check if it's monotone or not. Check this criteria. These are very important. If it's monotone, when we understood it's convergent. If it's not monotone, then we check something else. Is it monotone after a certain time? Yes or no? If it's a monotone after a certain time, it's like a monotone after a certain time and bounded. So therefore, it's convergent. If it's not monotone after a certain time, it's oscillatory. Fully oscillatory. Now the idea is oscillation, like when it will converge. The idea is that you will learn this. This is something called lim sub lim inf, and you will learn this that it's nothing but it's called oscillation. Okay, it's like this height of oscillation. There's a mathematical way to count it. Is it decreasing or increasing or decreasing? That's called oscillation height. If it's decreasing to 0, it can decrease it to 1. If it decreases to 1, how will it look like? So this length is constant. If the oscillation length, the height is decreasing to 1, that means the length is, it's not going to 0, but the length is constant. If it decreases 0, then it's, sorry, oscillation decreases to 0. If it's no, if it's yes. Example, yeah, found out, no. Also, an example of oscillation, -1 whole to the -1 whole to the power n by 1 by -1 whole to the power n. Like -1 1 -1 1 -1 1. You can see the oscillation height is 2. It never goes to 0. Okay. It doesn't converge, divergent. It's convergent here. So you can see that this is divergent. What happens if it's unbounded? If it's unbounded, it will either go to infinity, like let's say, like infinity, or it can be like it can go to infinity like this also. Going to infinity. It's going to infinity. See there it goes to infinity. Or minus infinity, or else it doesn't converge. Like for example, uh, it's unbounded, right? Like the size is increasing, -1 whole to the power n times n. Like it's like if you see in statistics, it's like the variance of the regression is increasing in some sense. Okay, the funnel size is increasing. It's like this. Funnel size is increasing. Doesn't converge. And this is interesting. We'll see that if a sequence is divergent, if and only if 1 by n is going to 0. It's natural because it's going to infinity. That means 1 by that will go to 0. For example, n is going towards infinity means 1 by n will go towards 0. So that's the basic idea. So therefore, if I say you, so therefore you can say for any convergent sequence, this is the path. Or it's like this is one path. or this path and then this path and then this path or then this path. So essentially you can track back, like if it's convergent, which one is it? It gives a complete overview of what's happening in a sequence, right? All of you understood this, yes or no? Everything clear? How a sequence is behaving altogether? So these are, yeah, Meenakshi.
So can there be any sequence which is monotone but not bounded, sir?
Monotone but not bounded. So let's see the decision. So it's not bounded, so it goes here in the divergent infinity. Monotone but not bounded. Yes, n equal to n. N is equal to n. So that's the homework for you. So the homework for you is to find 5 examples of each of this. So that you get to understand more. I will do one example of each of this. You have to do 5 more examples of each of this because it will make you understand and make you get a hold of functions and you understand all the diagrams out here. So what I will do is so I will show you that how I have made. So I have made a list for you. So this is one of the assignment problem. Can you see it? So you have to see 5 examples of each of this. Where also you have to find whether it's convergent or not. Right? This will help you understand like the functions better, where the functions are, how they're behaving, why these concepts are important. Like of course, so this was last year works. So this year assignment there's some extra because I have done it more this time, like oscillation height and all those things. Whatever examples you find out. Okay, this will help you understand your intuition about how a sequence is working internally. Okay, that's the best way to learn by examples. Okay, so also in this year's, so these are the assignments of yours. So there are quizzes, okay, quizzes like this where you are asked to find whether this is, so this will all uploaded, this will all be uploaded, whatever sequence. I have developed this using, found out this using the R code, and you can find out this is for example mode after a certain time. uh so so there's not more non-monotone here, but try to find out what it means. So by oscillatory I mean non-monotone, okay, remember that. Not oscillatory, so non-monotone. Um so what's the definition of monotone here? I will tell you. Monotone is, unbounded, oscillatory and non-monotone oscillatory is that you can assume that non-monotone is equivalent to monotone after a certain time. Now oscillatory is fully oscillatory, okay, that's the basic idea. For example, in this sequence, it's not, no unique limit is there. So understand, we are trying to understand the behavior of the sequence based upon these properties. So we have not done that yet. So what is the basic idea is that you have to find out. So we know what happens here. I have told you the diagram already, but you have to find examples out here, okay? So what I will do is this. You will do. So essentially, what are the properties there? Monotone. First is monotone bounded, okay? First is bounded. So how many properties are there? See, monotone bounded, no, not bounded, divergent to infinity. Bounded doesn't diverge to infinity. Okay. So 1, 2, 3, 4, 5, 6, like all this 1, 2, 3, 4, 5, 6, 6 types of there, right? So for all of them, like for all these nodes actually, find out for all these nodes, each of these nodes, find out examples. Okay, for each of those nodes, find those examples. Okay, I will give you one example each, and I will end the class. Bounded and monotone. Okay, um, simple, 1 by n. Monotone and convergent. Like not monotone, bounded, not monotone, but monotone after a certain time. Like n to the power 1 by n. I already shared that. It converges towards 1. It goes to 0. This one is simple. This one is sine n by n. The height is going towards 0. The oscillation. This one is good. Sine n or minus 1 whole to the power n. The difference is 1 always. Oscillation is 1. Sorry, 2. So observe this is also a part of this. Okay, so we are finding this is called leaf nodes. If you learn relation tree in machine learning anywhere in the future, you'll see something called nodes and leaf nodes. So this is very important for concept for you to know. For here, divergent is n. For here, uh, doesn't converge is sine n also. Not sine n sine n. Because it's not going to infinity. It's somewhere going to minus infinity, somewhere going to plus infinity. Like it's increasing like this. Okay. So that's it. So that's the basic idea of how the whole thing is working. And that's very interesting. That's really important, like, to understand how the whole technology of sequences is working. So in next class, I will be teaching you. So you understood how divergent happens and how divergent sequence looks like, how oscillatory and all these things happens. Okay. And next day in my class, you will learn those all algebra of limits and all those how to find the limit. Okay, all those important relationships, and we'll do problem solving. Okay, and in this upcoming Thursday class, you will learning about supremum. Okay, supremum of how to find the supremum. We didn't define it properly, but supremum concept is very important for you to learn. So one day will be only dedicated to make you understand supremum and infimum, because that's the basic idea of theoretical aspect of sets. Okay, and so probably since we are devoting more time towards basic understanding. We will take a probably few more classes. I will take a probably more extra classes on Sunday, Saturday. I will let you know if I accordingly need it. Otherwise, it will become a bit late. But it's okay. We'll take a few classes extra. 2 or more classes I need extra. And on the Friday class, there will be problem solving on the things that we are doing, and that's it. Okay. Based on homework problems and other problems that you have. Uh, that's it, and then this will continue till the end. But the basic idea of sequence is this is the the fundamental of sequence, understanding what it converge and the properties of it. And the other ideas are this, like, what's happening inside. Like, we'll see a sequence doesn't converge if there are number of different subsequence converge to different limits. And that's why the concept of lim sup and lim inf comes, because lim sup is the highest limit a subsequence can achieve, and lim inf is the lowest limit a subsequence can achieve. So this is all interconnected to each other. Okay, and then Bolzano stress. So it's essentially gives a glimpse of why a sequence converge, why a sequence doesn't converge. Okay, and the story behind it. And everything is clear in your mind. You will get a clear picture of everything out there. Okay. So thank you guys. I hope you liked it, liked our class, like this class. If you like this class, write a boom in the box as you do as a ritual at the end of the class. Thank you, Revan. Thank you, Disha. Thank you, Rahul. Thank you, Manegami. Ravi, Preeti, Shimanta Meenakshi. Thank you, Aditi. Thank you, Samruddhi. Thank you, Shurya. Thank you, Girish. Thank you, Disha. Okay. Thank you, Hemant. So I'm ending the class, and thank you, Gayatri. Thank you for staying in the class.